Hi, in this video I'm going to talk about linear regression. I'm going to start by defining the error measure we're going to consider. So similar to the last video with the perceptron, we're going to have the error measure be a sum over all the data points. So suppose we have data of the form x1, y1, all the way to xn and yn. Then we'll have the error measure be whatever our hypothesis says on xi, and we'll subtract the real value yi and we'll square it. So this will be our in-sample error. We'll make a 1 over n here. So you could imagine that if I have a lot of points, so maybe let's just say this is the so each of the xi's will be in our input space x, and maybe let's just say this is r, the real number. So then then I could represent each of these as just 1 point. So maybe I had points like this. Then let's say this is the underlying target function f. Then the errors would now be the squared of all these distances. So I would want to minimize all these squared. Okay, so this is my error measure. Then my hypothesis set is now the set of all functions h of x w transpose x. So this should remind you about the perceptron. We simply lost the sign. That's it. So it turns out that we can actually get an equation that computes the weights that gives us exactly the minimum error. Before we go into this, let's look into the IPython notebook. So in the IPython notebook, you'll see a brief introduction. This introduction will be basically what I just covered, and it'll also tell you that you can how you can compute the optimal hypothesis described by the weights w star. So suppose you have data that looks like, let's just try to restart this. So if I run the first line of code, I'll get some data, and this will be the function I actually use to create this data. This data is normally distributed around this line. So then the goal would be to find a line that would actually minimize the sum squared of all these points. So if we run the linear regression algorithm, we'll get something similar to this. So the least square error is given here, and then the real function is this guy, and the one we'll learn is rather close to this. Great. So this is basically what there is to say about linear regression. Except of course deriving this equation, and then also quite interestingly we can use an algorithm called gradient descent for linear regression. This is quite an important algorithm because we'll see it also for neural networks. This is the way we train neural networks, by gradient descent. So there's a little bit of introduction to gradient descent here. This will require computing the gradients, which we'll also do later. So if we try to run linear regression with a gradient descent, it looks something like this. So then again you get like a stepwise. So I might actually just comment that the gradient descent I implemented in this application is a batch gradient descent where the gradient is computed for all data points. You might want to read this entire document to understand what this means. Typically, you'll do something called mini-batch gradient descent, where we estimate the gradient by only looking at some of our data. This would speed the entire thing up and make it a lot more applicable. Great. This is all I wanted to say about linear regression. In the end, we'll also run it on, we'll modify it to do classification, and we'll run the breast cancer dataset. In the next video, I'll walk through these derivations.